All right, guys. So right now we're just going to try to go through some couple simple Lagrange multipliers examples. So the first one, I'm going to try to show you something with super simple algebra. The algebra gets harder from here, but let's do a simple one first. Then I'm going to try to show you how to cheat kind of using the grapher. So first things first, I want to try to find maximum and minimum values of f of x is 5x minus 3y, subject to a constraint of x squared plus y squared is 136. You might recognize this as maximizing a plane subject to the constraint that is a circle. So if I had to kind of draw a picture of what's going on, there's some kind of a plane, and on that plane is a circle. That circle is tipped, right? Because it's a circle in the xy plane, right? So it's actually a circle down here, and we've kind of lifted it up to our surface of our plane, so it's tipped. There's going to be a maximum and a minimum on that. There's going to be a point that's highest up the plane and a point that's lowest up the plane, right? So that's what we're trying to do. So let's write down some algebra to try to do that. So as soon as you're asked a Lagrange multipliers problem, you can pretty quickly jump to, okay, I'm going to call this thing here G of x and y, and then I'm going to get some equations. The place I'm going to get equations is I'm going to take the gradient of f, I'm going to set it equal to the gradient of g, and I'm also going to recall the constraint. So one of my equations is going to be this guy. The other equations are going to come out of this thing with the gradient. Oh, and I forgot a thing. I'm hoping you remember that I need a lambda in there, because even though the gradients don't have to be actually equal to each other, they just have to be parallel to each other. So that's where that lambda is coming in. So I'm going to get my equations. So first things first, I'm going to take the gradient of f. Like I said, this one's easy. So I got 5 and -3 are my gradient for f. I'm going to set that equal to lambda times the gradient of g, which is going to be 2x comma 2y. Easy peasy. So I'm going to write down my equations now. So set my gradients equal to each other, and now I'm going to get equations. My equations are going to be 5 equals 2x lambda, and -3 equals 2y lambda. And then we're like, okay, let's see. I guess I could probably, well, I feel like I could get rid of a lambda. So this is one where there's not actually a technique for these. There's not like a cookbook that you can follow. You just kind of have to do something. There's some tricks. One thing you could do is try to make everything equal to the same thing. That makes life easy. Or you can try to eliminate a variable. I'm going to eliminate a variable. So I'm going to say if I solve this one for lambda, that means lambda is 5 over 2x. I should worry right now, what if x is 0? I'm also going to solve the other one for lambda. So that, what the hell, we'll just plug it in. So I'm going to take this, I'm going to plug it in for lambda in there. So I'm going to get -3 is 2y times 5 over 2x. Now I'm going to say, what does that mean? Well, I guess I could multiply both sides by 2x. Oh, wait, I can cancel it too. Let's do that. Now I could multiply both sides by x. If I multiply both sides by x, I get -3x is 5y. Okay, so if -3x is 5y, I could take something about that and plug it into here, right into my constraint. So maybe let's do that. Let's get rid of y. So that would mean y is -3/5 x, right? That's multiplying both sides of this by a fifth. Wow, Joe, that's handwriting. Multiply by 1 over 5 there. So I'm going to get y is, oops, what am I doing? I need to plug that in the constraint. So we're going to go back over to our green, right, our constraint, and we're going to say that means that I get x squared plus 9/25 x squared is equal to 136. Okay. give myself a little more space. Well, I guess I could like combine like terms or something. So that's like 25 25ths. So that's like 34x squared over 25 is equal to 136. I said this algebra was going to be simple. Apparently, I didn't mean that the arithmetic was going to be simple, huh? Okay, so that means x squared is 136 times 25 over 34. Like, let's see, I guess I can cancel a 2 for sure. I don't think this is going to work out that nicely. Oh, what the heck? I'm going to show you. So here's a factor tree, right? So I'm going to take 136. I know there's a 2 in there. Let's see. And if I split it 2 ways, I get 68. Well, I guess I can split that 2 ways. So if I split that 2 ways, I get 34. Oh, shit. You can cancel 34 out of the whole thing. Okay, so that means x squared is 4 times 25. Hell yeah. That means x is plus or minus 10. 2 times 5. Right, I just square rooted each piece. Okay, so if x is give or take 10, well, then I guess I need to know what y is. Where am I going to get y from? Well, I'm going to get y from back up here. So there's going to be lots of back substituting here, right? So we're going to go back to this point. And so we're going to say, after going back to blue, right? Blue says y is negative 3/5 x. So that would mean y is negative 3/5 plus or minus 10. This is really a bad way to do this. So let me show you a better way. So I'm going to say y is negative 3/5 and x is either 10 or y is negative 3/5 times negative 10. This is the x is 10 case. This is the x is negative 10 case. So those are different, right? Because x isn't simultaneously both, right? It's not quantum superimposed or whatever. It's really just one or the other. So in the case that x is 10, then y is negative 6. And in the case that x is positive 10, y is negative 6. And in the case that x is negative 10, y is positive 6. Okay, so those are my 2 points, right? So ultimately here I've got 2 points. I've got 10 comma negative 6 and negative 10 comma 6. Those are my 2 critical points, right? These are the kind of interesting points. They're not really critical points. They're like the answers out of Lagrange multipliers, but what else? And then what am I trying to maximize? I'm trying to maximize and minimize 5x minus 3y. So I just need to do f at those points. So f at 10 negative 6 is 5 times 10 minus 3 times negative 6. Okay, that's 50, that's like 68. And f at negative 10 comma 6 is 5 times negative 10 minus 3 times positive 6. So that's like negative 68. Oh, cool. Seems like it worked out. So I feel like the max value of 68 is at 10 comma negative 6, and the minimum value of negative 68 is at negative 10 comma 6. Let's go check that quick. So let's see. So over here I have blank Desmos graph. So here's what I'm going to do. I'm going to graph 5x minus 3y equals v for value. And I'm going to add a slider for v. And then I'm going to put in here my other thing, so my constraint, which is x squared plus y squared, swear I can type, equals 136. So big old fatty circle out here, right? And then I'm going to slide v around. Oh, v's not moving very fast. I know these need to go to at least 70, right? So I'm going to do negative 80 to 80, and we'll do them by 2s, I guess. Okay, so see how we're getting close to the edge there? Whoop, too far. Pull that back, pull that back, pull it back. Okay, so it looks like that's the last place it touches. That's at the value of 68. And that intersecting point is 10, negative 6. Right, so I said it's got a maximum value of 68 at 10, negative 6. And if I pull it back the other way, that's right where it kisses. That's at negative 68. That's up here at negative 10, 6. Boom. Hell yeah. Just like that. Okay. So, oh, whoops. Drat. I should have kept that so I can put it in the video description. Oh, I'll remake it in a second. Okay. Other thing. So here's another problem that could be hard. Would be kind of annoying. I want to use a grapher to find approximate max min values of f of x is x squared y, subject to a constraint of x minus 1 squared plus 2y squared is 6. Let's see. That's some kind of a shape. I don't recognize x squared y as a shape. It's not one of my standards, so I'm not sure what it looks like. And then I'm subject to this constraint. That constraint's an ellipse centered not at 0. So I'm like, okay, well, we could start by calculating gradients, right? And this is where your like algebra hat's going to come out. This is going to get kind of rough. Not impossible, just rough. So here's an attempt to kind of guess at some answers. So here's a Lagrange like picture. So I've got my green constraint curve, and I've got blue level curves. So the blue level curves here, oops, that's not doing anything. So the blue level curves are generated here. They're from minus 10 to 10 by 2s. Let's make a few more of those. So let's do minus, oops. Let's do minus 16 to 16 by 2s. Okay, so you can see that I'm not hitting that one. Not sure what's going on there. We'll figure it out. Over here, yep, we got some values on either side. So I'm going to turn off the level curves because I don't think they're that helpful, actually. I'm going to turn this guy on. This is me trying to approximate, right? So this is a single level curve. And so I can see, like, we start out outside of the green ellipse, and then we scroll in and we hit it. So that's going to be an interesting point to us. And right now that intersection is at this value of 2.87, comma, negative whatever there, negative 1.129. And our value of our function is minus 9.3, right? So that's the first time we touch. Then if we keep going, we're touching in a couple of different spots here. None of that's actually interesting. We're getting here a spot where it first touches on this side, but that's at a value of a is negative 1.1. That's not going to be our max or min. It's just kind of one of the points that Lagrange would find for you. Then we're going to keep going. Oh, that was weird. So it kind of flipped over there. We're touching in way too many spots. Oh, there's a point where we're parallel. See that? Where it's tangent right there. So that's at value of 1.1. That again is not the maximum because we can see that this is still inside. So as we keep going, and right in there. Not surprisingly, that feels like, oh, yep. You can see I'm not quite on it because I'm still crossing at 2 points. So we could scoot it up a little bit. Oh, now we're past it. Scoot it inside a little bit. We're like, oh man, there's like, it's kind of in between these 2 points here. So I'm not getting an exact answer out of this because Desmos is actually like, the way I'm doing this is not the best way to do this. I'm just kind of using this to suggest what's going on, right? But we can get an approximation. Like if I get something that's basically 2.8 comma 1.1 or 1.2, I'm going to feel like I'm okay, right? Like I'm a little bit justified by this picture. And then we can see that as we get past that, it's probably gone for good, right? So I think the maximum and minimum of this thing are probably maxed at 9.3-ish and minned at also 9.3-ish. And then I know that if I did Lagrange on this, I'd also see these values at negative 1.1 and 1.1, even though those are only kind of locally interesting points. So I'm going to write down my answers here. I'm going to write down the max is approximately 9.3, min is approximately negative 9.3. Notice they don't always have to be symmetrical. The reason this one's symmetrical is that both my functions that I'm dealing with, so both the functions that I'm kind of dealing with here are symmetrical in y. So it's kind of flipsy, doesn't really change anything very much. It's actually the green constraint curve is symmetrical in y. The other curve, the purple curve f, is actually only anti-symmetric in y. So if I swap it, it flips to the minimum instead of the maximum, but it just interchanges the two. So not super crucial, just to know that it's not always symmetrical. I could make it not symmetrical by just adding something in here. I'm not going to do that. But if we shifted that ellipse up off of here, we'd have a different max and min. That's what I got for right now. Please note, I guess, I lied. That's not what I got for right now. Let's set up the algebra here really quick. It's kind of gross, but let's set it up so you can at least see what the algebra would look like. I need the gradient of f to equal lambda times the gradient of g, where g is my constraint, right? So this is g. So gradient of f is going to be 2xy comma x squared. And the constraint, so the gradient for the constraint is going to be, oh God, chain rule. Promise it's not actually bad. It's going to be 2 times x minus 1 to the power of 1 times 1. So 1 times 1. That's all redundant. Comma 4y. And so now we'd have some equations, right? So our equations that we have are 2xy is equal to 2 lambda times the quantity of x minus 1. We'd also have the equation x squared is 4 lambda y. And then we have our further constraint equation, which is x minus 1 squared plus 2y squared equals 6. So that's this guy here, made it right here. These other two equations, those guys came out of our Lagrange assumption. So these three equations together, you have to solve for the three variables, lambda, x, and y. Really, you only need x and y, so you might like solve this one for lambda and stuff it in that one. That gets you a relationship between x and y. You might be able to solve that one for y, then you can stuff all that crap into here. This is going to be kind of awful. Going to be a little gross. You're going to need the quadratic formula. You're going to do a bunch of foiling. Hope you're good at algebra, or at least patient. So there's some challenge here. These problems in particular end up with kind of tough algebra at the end. It's okay. You guys can do it. You just have to be really slow. Give yourself a big old blank sheet of paper so you're not constrained by space. I've seen people work problems like this. Instead of holding your paper in portrait mode, you might like pull the old switch to landscape. You got it. Get yourself, a notes app like this one where you can make an infinity by infinity writing grid if you need to. It's tough. No two ways about it, but you guys can do it. So thanks for watching. Feel free to toss stuff in the grapher if you're not sure. I will see you guys later.